All right. So, as we already know, the cryptocurrencies such as Bitcoin um, are based upon the two algorithms, right? The hashing algorithm that we went through in the previous three lectures also, right? So even though we learned about the hash one, which is hash 160, right? But I also mentioned that we just extend that a little bit, then we would have the current one that is the SHA-2, I mean, SHA-512, which is much better than the SHA-256 that Bitcoin is using nowadays, right? But Bitcoin 2.0 will move to the SHA-512 that I mentioned in the lecture. So basically, Bitcoin is a digital currency that is a distributed, decentralized digital currency system, right? And it started in 2008 by, a pseudonym, Satoshi Nakamoto, right? Okay, and let me remind you a little bit about what can we do or how can we use the hashing algorithm and also the crypto algorithm that I mentioned a little bit last time, right? That is the RSA algorithm. So today we will try to combine them and see how the two algorithms are used for the Bitcoin community. Okay, so now we know that Bitcoin is based upon the blockchains, right? What is a blockchain? It's just a chain of blocks. Very simple, right? And each of the blocks will have, say, the ID, which is the block ID number, right? And then the data, which is a set of transactions. We have, for example, Alice pay Bob 3 Bitcoins, right? And then Chris pay Doris, etc. And then the reward. So that's it. Everybody can access to all of the blocks. And there's a chance that someone try to change the contents of the blocks. And that is not possible because every block, like the previous block, we have the hash value, right? We hash it and then we keep it in the next block. That's it. If someone try to change something here, then the new block will have a new hash value and it will not be matched with the one that we store before. And that's it. We know that someone tried to do a dirty work here, right? So we will reject it. Everybody will have a copy of all of the blocks. So the only way we can be sure that the system is safe is that we have a mechanism that will ensure that no one can change anything in the chain of the blocks we have, right? Okay, so that is the first use. Okay, John, I saw your message here, right? Uh, I checked the university exam schedule at the beginning, and it was on the 6th. Actually, it can be either on the 6th or on the 7th. Yeah, so there are two options there for classes like us. So let me double check it to see if it's still there or if they change anything. So at the beginning, I checked the schedule and it was, I think, both 6 and 7. And then I picked the 6, yeah, because it was, I think, on the same day or so of the classes. Okay, but I will double check to see whether or not it has to be on the 7, okay? And if it has to be on the 7, then I will notice every student's that. All right. So I will double check it after the class, okay? And we'll let everybody know. We want to follow the university schedule, and that was what I did at the beginning. Not sure if they change it, but if they do, then we have to follow the new one, right? Okay, so all right. Now that is the first use of the hashing algorithm. Okay? And as I mentioned before, they use the SHA 256. Okay? We learned the algorithm starting with the SHA 160, and then we extended to the latest one, that is the SHA 512, right? So the SHA 256 is something in between. Okay, so now the second thing we want to do is that we want to know, say, here, when we have a block has all of the transactions, right? So that's it. Everybody can just have all of the transaction submitted to the block and then hash it. So we can have the hash value here. And then have that value for the next block if we finish this block, right? And then everybody will start to build the next block. So everybody can hash this. So what does it mean? We have millions of users and everybody can hash it. Then who will have their work accepted as the block for everybody else? If you can hash the block, I can hash the block, right? Then, I mean, there's no reason for giving me one Bitcoin when everybody can hash it, right? So you can say that I can hash it. I should have one Bitcoin as well, right? And then I hash it, and I also say that I want to have one Bitcoin for this work as well. So who should have the reward, and then who should have their block be used by everybody else? So that's the competition here, and it's what we call mining the Bitcoin. Okay, so mining the Bitcoins means that here we have a block of transactions. We need to find a person who can earn the reward by doing something. Okay, doing something is as follows. We know that here we have a block, we can hash it, right? But to make it harder for people who can try to hash the block, we will use what we call the nonce value. Okay, so here we have we add one thing we call the nonce number that is just once. Okay, or I mean, most of the time we call it nonce. What does it mean with nonce? Non is an arbitrary number that has 32 bits. Okay, 32 bits. So when we add this nonce in, we can hash the block, right? It has a digest, meaning the hash value. So what is the point? The point is that for 32 bits, you know that we have 2 power to the 32 different values, right? And the nonce value that after you hash this one that has the 0 at the beginning, 32 bits 0, then that nonce value will be used for hashing the block. Okay? So now, if I want to find the nonce so that after I hash the block, I have 0, 0, 0 at the beginning, 32 of them, then I will win. Okay? Meaning I will have the reward. But finding the nonce so that when we hash it, you have the 0 at the beginning is unpredictable. It means that I have to generate random values for the 32 bits of nonce here. I can try with 0, 0, 0, 0, and then 0, 0, 0, 1, and then 0, 0, 0, 1, 0, etc. Okay, I have to try, say, 4 billion. Actually, they use one bit for the signature, so it will be just about 2 billion cases. So now the first one who generate the nonce value that when we use it to hash the block with the smallest value, theoretically it's very hard to find a nonce so that we have 32 zeros at the beginning. So usually we just have the smallest number. Okay? For example, if I can find 30 zeros, say after 10 minutes, then I would win, right? Otherwise, yes, exactly, Kayla, right? So it means that I have to mine the nonce number. And if I can find the nonce number that I have the smallest value, meaning the biggest number of 0 at the beginning of the digest, then it's a proof of work. Okay? So you see, Bitcoin or mining a Bitcoin is very simple if you look at that from an algorithmic point of view, right? So that said, okay, here I have a set of transactions. I just have to randomly generate the nonce so that after I run the hash function, I have many 0 at the beginning, then I will win. So that's why mining means simply generate a nonce value randomly, run the hash, and then find out whether or not we have the smallest value, right? Usually, if we have a value that is smaller than the average of the previous 2 weeks, then we will have a reward. All right, so now you know, okay? What does it mean with mining a Bitcoin or mining, say, a cryptocurrency? I mean, a crypto coin, right? It's super simple. The only problem we have is that we have to generate billion of different options, and then for each of the option or each of the nonce value, run the hash function, right? And then see whether or not we have a small value for the digest. Okay, super easy, but we have to do it many times. That's why they have the GPU, right? GPU has thousands of small computing core, and each of the computing core will do one of the hashing function or one of the hashing algorithm, and then we will compare and find out which one is the smallest. So from the algorithmic manner, Bitcoin is pretty simple. Okay, it's pretty simple, and in fact, after learning about this, we can design our own Bitcoin. And if you are interested, nowadays we have what we call the Bitcoin 2.0. That is where we will learn, or where we will try to do research to see what kind of algorithm should we use for finding the nonce, right? Or what kind of hashing function should we use? Nowadays, obviously, we want to move up to the SHA-512 that you already learned, right? Okay, so it's what we have right now, and you can also have the idea of what does it mean with mining, right? Okay, I can skip this one. I showed you last time, right? So every block, when you look at, for example, blockchains.info, I showed you last time. Not sure it is still here. Okay, here. So we have the current situation on the world now, right? So we have many blocks here, and each of the block, you see the nonce, right? The nonce right here. Yeah. So every block should have a nonce that has the smallest digest as a proof of work. Okay. All right. So now the second thing we want to see is that how can we use the RSA or private public keys in order to maintain the correctness, right? Or maintain the accuracy of each of the transaction. For example, Alice PayPal. Okay, we want to know whether or not it's coming from Alice, right? And how can Bob have the payment, right? Okay, so that's what we want to know. So everything is distributed on the internet. So we need to know, is it Alice who paid? And then is it Bob who will receive it? Even though I'm not Alice, I'm not Bob, but I can see this information. Can I use this information in order to get the money, right? Everybody see it. So can I simply take the money from them, right? So we have to be able to prevent that, right? So that said, the payment here is intended for Bob. So Bob is the only person who can get the money, right? Even though everybody can see the transaction, but only Bob can actually decode the message here. So the message here, we have some encrypted information that only Bob can decrypt that, right? Okay. All right. So that is what we have with the public-private key. So last time I showed you one example for how to generate the key, right? So we have the algorithm that we can generate the, say, signature. We can generate our public key and also our private key. And then we will use the public and private keys to encode and decode all of the information, even though the information are published on the internet, but only the intended one can interpret the information. Okay, so that said, everybody on the, say, cryptocurrency world should have a pair of key, public and private, right? For example, Alice will have her key, right? So there are two keys, the public keys that will be posted on the internet. Everybody will know the public key of Alice. So that said, if the public key is here, then we know that it's for Alice, right? Alice will have a private key as well, that she can use for producing the signature. Okay, we will learn a little bit about that right after one or two slides here. Okay, so that said, if Alice want to send a message to Bob, right? So first, she will use her public key to encrypt it, right? Okay. Then, well, actually, if I want Alice here, want to send it to Bob, okay? Then there are two different situations, but let me go one after the other. Okay? So Alice will use Bob public key. Okay? Alice will have public and private key. Bob will also have public and private key. Alice will use Bob public key to encrypt it. Okay? She can do that because the public key of Bob is published on the internet. Everybody know that, right? So she can encrypt the message using Bob public key and send it. Okay. So even though everybody can see the encrypted message, but we cannot understand what does it mean, because only Bob, when he used his private key, then he can decode that, right? So last time I showed you one example for how to decode using a private key, right? So that is one thing. Okay, that is one thing that when Alice want to send a message to Bob, and only Bob can understand. So, for example, Alice will send the let's say she has a Bitcoin, right? And then it means that she knows the ID of that Bitcoin in her wallet. And she can send that information to Bob so Bob can withdraw the money from her wallet. So she will use the public key of Bob, right? Encrypt the Bitcoin's ID and send it to Bob. So everybody can see the text, the encrypted text, but only Bob can decode that, right? And keep in mind that Alice does not know anything about the private key of Bob. Okay? She only know about her own private key, and she can use it for signing some documents. And it's the next step we will see. Okay, so now how do we have the public private key? So last time I showed you a few examples. So that is from my software, right? Okay, so here we can generate our own public private key. Okay, and then here are the key I just generated. So it has say the public key. Yeah, it has two parts, number n and then e, and then private key number n and then number d, right? So when we try to encrypt this one, computer science, we have two different encryption, okay? Forward encryption and backward encryption. Forward encryption is what I just explained to you, right? So when Alice wants to send a message, she will use the public key of Bob, right? Encrypt that and send it. So for example, here we have the message is computer science, right? So we want to encrypt this one. So that said, we can use the public key to encrypt this one. So here is what we have. Let's say the message is here. And then we encrypt that. So we will have this message with the numbers here, right? So we can decrypt that by using the private key. Yeah. So after we decrypt that, we have the message computer science back. Okay. So now, how it works. So first, we select two large prime number. Okay. About the same size. Why about the same size? Because it will be much harder to guess those numbers. Okay. So that said, usually the two prime number will have between 512 and then 2048 bits. It means that if we have our public and private key using 512 bits, if someone wants to guess, right? Let's say what is my private key from the public key I posted. It may take them 100 years. If I use 2048, then with all the computers on the world we have right now, it may take 1,000 years. Okay? So that's why we want to see if the public-private key is safe enough for transactions in Bitcoins or any crypto coins, right? Okay, and then after that, we try to calculate the public and private key, right? So it's very simple. We just want to select a number that is the coprime of phi n, where phi n is q minus 1 times p minus 1, right? So E here, if you can see from the algorithm, I will just find out a bigger value of E. Okay, so start with E is 2, whether or not E can be used, and then increase it, right? But usually we want to keep the E here big enough. Okay. All right, and then after that, we find out a D, which is the public key we want, right? So we can keep E as our private and then send out the D as the public key, right? The only requirements is E and D co-prime, meaning that they are modular 1 with respect to phi n, where phi n is here, right? So the algorithm is pretty simple, as you see from my implementation here. Okay. So first I take two prime number big enough, right? And then I have the 5, right? And then I choose E, which is big enough. I started with 1/4 of the n. Okay. So that's it. I will check whether or not the GCD of E and P is 1, GCD of E and Q is 1, and GCD of E and phi is 1. If not, then I increase E. Yeah. Eventually, we will find an E that satisfies the condition, right? And then I find out what is the co-prime number of E, right? And then I post, here's my public key, and here's my private key, okay? I can say that E is my public key and D is my private key, or vice versa. It doesn't matter, okay? I can say that here's my, E is my private key and D is my public key. It will work also, Okay. So the point here is that it's easier for me to generate the keys. But if someone see the number n and number e, it's very hard for them to find out what is d. Okay? It's almost impossible if they don't have, say, all computers on the world working for 100 years. So, however, it's only true for the current computer systems. And we cannot guarantee that if we have a quantum computer, right? Because quantum computer works in a totally different manner. And it can do many computations at once. So that's why everything we are doing here for the cryptography may not be true once we have a working quantum computing, okay, or quantum computer. All right, so the algorithm is pretty simple, and it's based upon the assumption that if we have, say, a number n and a public key, it's very hard to find out the private key. Okay, that is the idea of the cryptography we have here. Okay, all right. So this one I already mentioned. So a simple example is that if we have P is 11, Q is 7, right? Meaning that we have two prime numbers, right? P and Q. We multiply them, we have 77. Okay, and then we multiply P minus 1 is 10, with Q minus 1 is 6, is 60. So that is what we have for 5. Okay, and then after that, we can have our E is 37 by checking, right? As I mentioned before, we can start with E is 2, see whether or not that GCD with P and Q and phi are all 1, meaning that they are all co-prime, right? If not, then increase, 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 and then you can see that 37 and P, GCD is 1, with 7, GCD is 1, with 5, GCD is also 1, right? And then we can find out D, which is the co-prime of E, right? So we have E times D is 481, modulo 60 is 1. That is how we can find E and D. Okay, so once we have that, then we can encrypt a message. For example, M is 15, right? Then encrypt that by take M power to the E and modulo M. Yeah, that is, we have 71. That is the encrypted value of 15, right? And when we decrypt that, we simply have here the encrypted value, take the modulo of D and take modulo, power to the D and take modulo N. Okay, everything we have modulo N, right? Where N is 77. Okay, and when we take that, we have back to 15, right? So that is what we have. Or vice versa, from M, if we take modulo of D, power of D modulo N, and we encrypt that using the private key, that's fine. That is actually what we use when we have the signature, okay? All right, so now how can we find the signature, okay? Or how can we generate our signature? So when you want to join a Bitcoin platform, they will offer you, yeah, I can generate the public private key for you, and then I can generate a signature for you, okay? But as a computer scientist, we already know the algorithms, so we can do it by ourselves, okay? Or we can have a program that can offer that service to anybody. So how do I generate a signature? Okay, so here is the message. I hash it. We already know how to hash, right? For example, by using SHA-1, right? So we have the hash value, and then we will use the private key to encrypt that. Then we have our signature. Okay? The signature here is for this message. Okay? So if we have a different message, we will have a different signature. Okay? And now, when we use the original message together with the signature, then we have the signed message, meaning that, okay, here is my message. Okay, we can verify that the message is coming from me, not anybody else. Okay, so when I say that, here is my message, you know my public key, right? Because everybody know that. So you can verify that the message here comes from me, not anybody else. Okay, how can I do that? Okay, so let's say I send a message to every student. Okay, by sending the message and my digital signature. When you receive this, meaning you receive the message and my digital signature, how did you know that the message coming from me, not somebody else who said that is from me? Yeah, you can use my public key, right? Because you know my public key. I post it on the internet. So that said, if you use my public key, right, then you can decrypt this digital signature, right? Because if you use my public key, you will have the hash value back. Yeah, right. Now, once you have the hash value from my signature, you can compare that with the hash value when you hash the message. When you hash the message, you have another hash, right? And then you use my public key, okay, you have another hash. If the two hash values or the two digests are the same, then the message is actually coming from me, right? Because here, nobody can know my private key, only me. So I use my private key to encrypt that as my signature. Everybody can use my public key to decode that, having the hash value back. And the hash value here should be the same as the hash value from the message I sent together with my signature, right? So that said, if someone change the message here a little bit, then you will see that the hash value when we hash it will be different with my signature, right? Okay, so it's very simple. Yeah. So, but that's why we have the digital signature. Yeah. Every document we can sign it with our digital signature. Yeah. And that is enough for saying that the signature is from me for this message. Okay, let me go back here a little bit. Okay, this one. All right. Now, everybody has the chat, right? I'm not sure if you are still using that, right? I don't use chat anymore, but some people still use the chat, right? So, what does it mean with the information we have on the chat here when we translate those information into what we have for Bitcoins? So here you see that the check is from this person, right? So what does it mean? It means that we can use a public key for that person, right? Okay. So on the check, you see from this person. Instead of having that information, we can use the public key. Everybody has a unique public key, right? And then pay to the order of someone. All right. So here's the public key of the payee. I mean, the payer, right? So here's the public key of the receiver, right? And then we have the date, the amount, right? And then some message here. And finally, sign the check. Okay. So here's the question. Yeah. For signing the check, we just learned about the digital signature, right? Now, when you see a check, we know that someone tried to steal the money by, for example, scanning the signature on the check, right? So they can have the check, blank check, and then try to scan the signature or try to redo it by hand. Okay, and then write another check by copying the signature of the owner here to another check. Question: can we do it in the Bitcoin environment? In other words, we know one transaction here from this payer. Okay, we know his or her signature. Can I just copy this signature so I can have another check writing to me? For example, this person pay me 1 Bitcoin, right? Can I write another check or produce another check using the same signature here for exactly the same amount? We cannot do that, right? Yeah, very good, Caleb. Because unless when we have a paper check where we can sign exactly the same thing, the signature, the digital signature will be different. Okay, because here we have the signature here is produced by using the payer private key that I don't have. Hence, when I try to make another check, some information will be different. For example, the date may be different or the check number will be different, right? So let's say I want to write a check number 506. And this number will be used for producing the digital signature, right? Meaning I have this number, yeah, everything here hashed, and after hashing that, I apply the private key, right, of this person that I don't have. and hence I cannot do it. Okay? If I do it, then when I use the public key here to decode it, I don't have the same hash value. Okay, so that said, the signature on a digital check is totally different every time we produce a check, okay, or a payment or a transaction. Okay, so you can see now using, say, blockchain transaction is much safer than using the paper checks, right? Because we can be sure that only me can sign this check, right? So different check, we have different signature, even though they are different, but after using my public key, people can recover the information to prove that it comes from me. Yeah. All right. So basically, it's something like this. Okay. So here's the information I have, right? So for example, I have a document like a check, right? So I can hash it. Okay. So after I hash it, I use my private key, or here in this case, Ross, right? So he will have a document, hash the document, use his private key, okay, not the other side's private key, right? Because he does not know, right? Or he cannot use the public key of Rachel, right? Because he wants to show that, okay, he wants to sign the document, not Rachel. Okay? If he use public key from Rachel, Rachel cannot be sure whether or not the document coming from Ross. Okay? So it's two sides of the problem, right? So on the one hand, we want to be sure that we send a document to the other person. And the other side is that Rachel wants to be sure that the document come from here. Okay? For example, when we want to have a contract, right? So Rachel wants to be sure that the contract is signed by Ross, right? And also, Ross wants to be sure that the information here is sent to Rachel only. Okay? So it means that it may involve one more step, actually. Okay? So here, once he has the document, right, he can encrypt it using his private key and then send the document together with the signature to Rachel. Rachel can use Ross' public key to be sure that this message is coming from Ross, right? Okay. Now, question. For this kind of communication, we can only be sure that Rachel received the message from Ross. But do we sure that Ross' message can be seen by Rachel only? This communication, can we be sure that the communication is intended for Rachel only? Let's say if I receive this one, can I see the document? I'm not Rachel, right? But this one sent over the internet. So if I can see this one, can I see the document? And can I know that it's from Ross? Anyone? A good question. So it means that in this situation, Rachel cannot use her private key for anything, right? And that said, the message here is intended for everybody, not only Rachel. Okay? So now, what should I do if I want to be sure that the document together with the signature is intended for Rachel only? He will have to do one more step, right? Using Rachel public key. And then decrypt it, right? And send to Rachel. So one more step using Rachel public key, and then encrypt it and send over the internet to Rachel. So in that situation, only Rachel can use her private key to decode this one first, right? And then use Ross public key to decrypt to see whether or not she has the same hash from the document, right? So in that situation, it's a totally secure communication, right? Only Rachel can receive the document, and Rachel will know that it's actually coming from Ross, nobody else, right? So that is what we have for the security of their transactions or the blocks. Yeah, it's called the double encryption, right? Yeah. So we have the public key, I mean the private key here is for ensuring that it's coming from Ross, right? And then the public key here is means the message is intended for Rachel, right? So it's from one person to the other person, right? And even if we can see the communication, we cannot understand or we cannot know what is inside the document. All right. Okay, so that is basically all we need to know about Bitcoins and blockchains. Okay, so now at this point, I hope you understand a little bit about the cryptocurrency. Okay, so any question about the blockchains and the cryptograph and the cryptocurrencies? Okay, so now you understand, I hope you understand more about what's going on with their Bitcoins and all of the digital cards, right? So now you will be, I mean, I hope that the reason why I want to introduce this one, because Bitcoins and say cryptocurrencies are getting more and more popular. And as a computer science student, I hope you can understand the algorithms behind them. And after the lecture here, you will see that, in fact, the algorithm behind the Bitcoins and the blockchains are very simple, right? So you understand them, and also how do we secure the transactions over the internet. And that kind of security is used not only for Bitcoins, but also for network securities. And this is what I'm interested most, right? And also the algorithms for the quantum computing is actually what we are interested most nowadays. Okay. All right. So that's it for about the blockchains and say crypto coins, right? Okay. Now the next part is about how to prepare for the final exam. Okay. So for the final exam, at this point, I plan to have about 4 questions because you will have 2 hours for the final exam, right? So 3 questions will be about the dynamic programming techniques. And for that purpose, I gave you the homework exercise number 4, right? So I will go through your solutions. I saw that some of you have perfect answers, right? But I will go through each of your answers to see if I need to give you some, say, explanation about whether or not it's correct or how to correct if you don't have the correct answer, so you can be ready for the final exam. So final exam, like John mentioned before, okay, I will double check to see if it's on the 7th. But if we can have it both on the 7th and the 6th, then I will prefer to go with the original one we have. Okay, and that is what I have when I check the university schedule at the beginning of the semester. Okay, so 3 questions will be about the dynamic programming. So practice with the algorithms we learn in the class. So we learn 3 different problems, right? And keep in mind that dynamic programming is just a programming technique. It's similar to divide and conquer and recursive algorithms, right? So that said, dynamic programming, we have to understand how to break the problems and how to remember the results of the smaller problems in order to build up the answer for the bigger one by memorizing the smaller results, right? Okay, so you will have 1 questions a little bit about Bitcoin. Okay, so it will be pretty simple. Basically, I ask you many questions during the classes, right? For example, what is the complexity of the hashing algorithm, right? And also today I ask you a lot about whether or not we can just copy the digital signature from one transaction to the other, from one digital check to the other, right? And also whether or not a message, when we send it, is intended for the other person, right? Or how do we ensure that the message is coming from one person? Like, okay, someone say that Dr. Tran sent us a message like this, right? So how do we know that it comes from me, right? So if I sign that, how do I sign that, right? So those one will be very simple, but just want to show that you understand some basic concepts about blockchains and bitcoins, right? So during the class, as I mentioned, I asked many questions. So just if you did not attend the class, then you can review the video that I posted before. Okay. All right. So those are about the final exam. Okay. So anything you need me to help you to prepare for the final exam, like you want to have more practicing question for dynamic programming or anything. Okay, and keep in mind that when you have the dynamic programming problem, you will not have the same question, right? Because I implemented all of the algorithm, and I can run on my algorithm, for example, Tower of Babylon here. I can run it, and then I can generate many different examples. So the best thing to prepare is to understand the algorithm, and then practice it with what I gave you in the exercise number 4, right? So when you see a new problem for example, that assembly lines, right? And you know how to apply the algorithm. Okay, so the point is understanding the algorithms and applying the algorithms. Okay, and I know that some of you did very well when I asked you to implement the matrix chain algorithm using dynamic programming. So some of you did very good there. So it shows that not only understanding the algorithm, but you can implement the algorithm. Okay. Same thing for the blockchains and bitcoins. If you are interested, I can give you some more reading so you can implement your own, say, hashing algorithm, your own, say, encryption algorithms, right? So that's why you see that nowadays there are many different crypto cards, right? So how can I do that? Follow the algorithm you learn here, right? It's pretty not very hard. Okay, so the only problem is that how they can attract the investment, so they can set up the system and ask everybody to use it, so they can collect the fees, right? Is actually not very high scientific contribution, in my opinion. Okay, so I think this class will be our last class. Okay? Unless if you want me to give one more lecture on Thursday, then just spend time to review the lectures, review the video, and I will use this Thursday as a reserve one, just in case someone wants me to work one-on-one with you, right? So if you want to talk with me, then this Thursday from 3:30 to say 4:45, I will be available. So if you want to talk with me or have one more one-on-one lecture, then I will be available. Okay. Anything else? No? And hopefully you will you will do a good job for the final exam. Okay? And don't hesitate to contact me if you need my help. All right. Take care and bye-bye.